not the case. Would we all agree that there's less stuff that we know than what we actually do know? Somebody asked me the other day, they said, Mr. Guess, you know all mathematics. I like started laughing. They're like, why are you laughing? That's just such a dumb question. Like of course, there's so much mathematics I don't know. I mean, you just don't.
What percent of mathematics do you think you know?
1 over infinity.
Oh, you're so funny.
Okay, so excellent point. Thank you for your question. We'll see what you do know. Turn to the person next to you and see if you can tell them what is the fundamental theorem of algebra. Go.
Probably something that has to do with something about algebra.
Watch
this.
I
was gonna say. It's not recycling because it's not.
That's me too. Yeah. Well, was it plastic?
It was handed I was aiming for the trash to get it over.
Yeah, at least you made it in.
Oh my goodness.
You don't have to write that down, but you can glance at it. Who can tell me what the fundamental theorem of algebra says about that? And it says precisely 3 things. And by the way, this was all of chapter 3 last year. You absolutely loved it, and you did amazing on it. What 3 things does it say about that? Give me one.
It's going to have 4 outcomes.
4 solutions or roots, right? There are 4 different things that we could plug in for x such that it would produce 0. Whatever degree you see there, that's how many solutions there are. That's the first thing it said. Everybody good with that? The second thing it said that every polynomial can be written in factored form, which is pretty cool. Okay? And then the third thing it said is this, is that if it has a degree of 4, that means it either has 4 real solutions or
4 fake solutions.
2 real.
2 real and 2 imaginary, or
0 real.
0 real and 4 imaginary. Because the imaginary solutions always come in pairs. It says the imaginary solutions always come in pairs. If one is a solution, then so is the conjugate. Okay? Really, you know a lot of mathematics. You really, really do. Today, that's the fundamental theorem of algebra. It's super cool. Today you learn the fundamental theorem of calculus. There are 2 parts. There are 2 parts. It is weird. Just about every math teacher I've ever met and professor, you always teach part 2 first. And then you teach part 1 next. Okay? We'll mix them up a little bit. Today I'm going to give you something, an explanation. It's pretty cool. After I give you the explanation, we're going to do fundamental theorem of calculus part 2. And you're like, oh wow, that's one of the cooler things I've ever seen in my life. Okay? And then we'll go back and teach one at a later time. So here's what we have. A brief reasoning behind the fundamental theorem of calculus. I want to be clear, this is not a proof, but it's a pretty good explanation of why it is what it is. I'm going to call this, y is equal to f of x. Okay, that's our function right there. Okay, it says f of t. Okay. So what I'm going to do is I'm going to talk about, again, the fundamental theorem of calculus. In a lot of calculus that we're doing right now, it refers to area bounded underneath a curve. So I'm going to bound this by a x, and we're going to do a third boundary. X plus h.
Are these random?
What?
Are these random places?
Yep. And what I'm going to do here is I'm going to write an expression for 3 different areas that we have, okay? First of all, what is the distance between x and x plus h? It is h. So can everybody see a little bit? I know you don't see the whole way, but as I introduce class talking about f of x plus h minus f of x all over h, you see the x plus h, and the h, right? I mean, that's going to come into play in our reasoning here in a second, okay? And I'm going to use a very kind of non-calculus way of describing this. We're going to say that this area right here is the area bounded between A and X? Thank you. I work hard at this stuff. So, and then the second thing that we have is we have another area right here. I'll call that the red one, and that's the area bounded from X to X plus H. Very good. And then finally, I'm going to talk about a third area representation, and that is going to be the whole thing. That will be the area from what? A to X plus H. And so that's our setup, and we're gonna kind of focus on this red part here eventually. But right now, I want to write an expression for that red area, namely that the area from X to X plus H is going to be equal to. Can somebody tell me what I could do with my other two areas that would equate the area from X to X plus H? Yes, Lil.
I might be wrong.
Well, that's the great thing is we celebrate taking chances because we're wrong a lot. So what were you thinking?
The area of the top minus the area from the black.
Yeah, if you take the purple expression minus the black expression, you're going to get the red expression. Everybody agreed? Let's write that out then. Thank you, Lily. And again, Lily, the most important thing is that you took a chance there. Thank you for taking your chance. Minus the area from A to X. Haven't lost anybody yet? Okay.
How do we solve that?
Well, right, yeah. So we're going to do something that's kind of interesting here. We've been finding area of rectangles. Agreed? Area of rectangles. So I'm going to make a rectangle out of this. I'm going to draw a red rectangle, just like that, right there. Okay. And does everybody agree that's not the exact area from X to X plus H?
Yes.
But it's close, isn't it? Okay, so we're going to say that that area is approximately the same as the area from A to X plus H minus the area from A to X. It's not the same, but it's close. And I can find the area of that rectangle, can I? How do you find the area of the rectangle? Base times the height. As Aiden said, the length of the base is H, and the height is simply whatever the function is evaluated at X. Everybody agreed? All right, so if we take the height times f of X, that will produce an approximation of that area. And that's what we've been doing, is we've been approximating areas, have we not? Well, I'm going to do something here. I'm going to divide both sides by H. And I get f of X is approximately equal to the area from A to X plus H minus the area from A to X all over H. Does that look a little bit familiar? Addie, what are you seeing?
Oh, the X plus H and the minus X over H.
Yeah, so she sees the X plus H, she sees a subtraction sign, she sees an X, and she sees an H in the denominator. What's the only thing that's missing? Limit, right? So I want you to look at this, okay? Suppose that we make H smaller. Suppose we make H smaller, we draw those two together. Would you agree that as H gets smaller, that the rectangle becomes a better estimation of the actual area? So we could say that f of X turns from an approximation to an absolute equals the limit as H goes to 0 of the area from X plus, or A to X plus H minus the area from A to X all over H. So when we allow h to go to 0, it becomes exact. And all of a sudden, what we have here is something really, 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 really interesting. That is what we just looked at the beginning of class, is it not? So let's write down, what is the function? What's in place of our f of x? Everybody agree that that's in place of the f of x?
Yep.
So what's the derivative of that?
Good question.
Wait, what is that again?
We have rounded from a to x plus h.
The derivative of this
Is the same thing.
is that. Does this thing not find the derivative?
I suppose.
And it says it's equal to that. Yeah.
Can you go back, wait, what you just wrote, and then over one more to the left? Yeah, how did we get that again?
Yeah.
So f of x, okay, great question. All right, so let me interject this because I see a couple people lost us here. I do want you to see this, so please pay attention. So we had our rule. We have the limit. Actually, I'll back up one more step with that. I'll say the derivative of a function is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Everybody agreed? So if we write this out, the limit as h goes to 0 of x plus h quantity cubed minus x cubed all over h. Notice that in this situation, our function is what? X cubed. The function is whatever sits there. You see that? What's the derivative of x cubed? This thing will come out to produce 3x squared. You see it? So as we rotate back to this, okay, what this says is the area function is our function. What's the derivative? F of x. In other words, the derivative of the area function ends up being the function that's right above it. So, you'll connect this together, trust me. F of x is the derivative of the area function. So what about the area function? The area function is the antiderivative.
And that's like when you do a derivative backwards.
We do a derivative backwards. I'll make sense for this, I promise. Look at this. Suppose we have x cubed. What's the derivative?
3x squared.
3x squared. So that's like f prime. This is like little f. We're wondering which is the one back here. We'll call it big F. What's the thing you take the derivative of to get x cubed? Talk amongst yourselves. See if you can think of what's the thing you take the derivative of that would give you x cubed. You're trying to back up. Think about it. Talk to your peer. Try to come up with something. Go. Talk.
Go ahead.
Could be this. Because if you multiply that forward, it could be one.
But 1/4
X to the third.
minus
Oh, yeah, so it'd be 1/4 X.
Oh, 1/4, yes.
Yeah,
It's just minus one.
Yeah, so 1.
Addie, what'd you get?
1/4 X to the 4.
Everybody knows it's gonna be x to the fourth, agreed?
Yeah.
If we drop it over 4, does everybody agree that if you do that and take the derivative, you're gonna get that? Yeah. So it turns out that if you want to find the area, you don't have to do an infinite number of rectangles. All you have to do is find the antiderivative, and that will find the area for you. Hands down, that's it. That's all you have to do. So what is the antiderivative of x to the nth? Very simple. F prime of x is equal to, what is our rule if we take the derivative?
And x to the n minus
N times x, whoops, sorry about that. N times x to the n minus 1. So the antiderivative, big F we'll call the antiderivative, that happens to be x to the n plus 1 divided by n plus 1. All you do is you add 1 to the exponent and you divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Yes,
I have a dumb question.
you don't have dumb questions.
No question is dumb.
Yes.
Farther. So that f of x is different than that f of x.
Yeah.
What?
In this case, this f of x is referring to the derivative of this piece.
Yeah, and then that one's just
Okay.
referring to the a.
Yeah, I mean, so our big and lower f's, they won't get mixed up anymore in context of this problem. Don't try to relate the two together right away. No. Just understand this idea, that, and this is the big idea, the area function
Okay.
is the antiderivative of the function.
So don't worry about f of x as being different.
Not right now, nope, okay? So, if you flip to example 1, okay? We're gonna skip fundamental algebra calculus part 1. You've seen a little bit of it. We'll reveal the rest of it later on. By the way, you have a day to work tomorrow on this assignment, okay? We're taking our time, but you're gonna have a day to practice in class. We do not anticipate playing students tomorrow. Okay. We are sure, okay?
Maybe during the last 5.
So it says find an antiderivative of the following. Very simple. We do big F of x is equal to, and we already found the derivative of x cubed. Let's try it again. You add 1 to the exponent, you get 4, and you divide by the new exponent. Simple as that.
So we're using big F's for the antiderivative.
Big F will refer to the antiderivative of little f. Big F is equal to, I have 5x, I raise it to the 5th, and I divide by 5. And what do you get? Does it make sense to everybody that x to the 5th is the antiderivative of 5x to the 4th?
Yes.
You should never get that wrong. And here's why. Can't you always just check your answer? Like, just take the derivative of x to the 5th. Is the derivative of x to the 5th 5x to the 4th? Yeah, so you know it's right. Okay? So you can always check it. The next one, I have big F of x is equal to 4x to the 7th over, and there's no simplifying, so that's it. Uh-oh, what's different about the next one?
It's fraction.
It's a fraction, okay? And so we're going to rewrite this as 3 over 2 times x to the negative 3. So big F of x is equal to 3 over 2 times x to the negative 2. You have to raise it 1. That's a mistake that's often made. Divided by negative 2. So you end up with 3x to the negative 2 divided by negative 4, otherwise known as 3 over negative 4x squared when you drop that back down into the denominator. Antiderivative. Here's the crazy thing as you go on. I mean, you guys have seen your first glimpse of an antiderivative. Derivatives are easy to find. We can find derivatives basically anything. You give me a problem, I'll find the derivative. There are so many functions out there, I can't find an antiderivative. I've got no way of finding it. It's super challenging. In fact, much of Calculus 2 is devoted to what do we do if we can't find an antiderivative. Statistics, the study of statistics, you guys used to the bell curve? You guys see the bell curve in your psychology class and stuff? That bell curve is something that we cannot find an antiderivative for. There's different methods by which they do it, but once we develop that, all of a sudden statistics start to explode in its applicability. So let's actually do the fundamental theorem of calculus part 2 now that we know how to find an antiderivative. Fundamental theorem of calculus part 2 says this very simply. The integral from a to b of f of x dx. We've been doing that, haven't we? And we've been doing that by finding the area of an infinite number of rectangles and adding it up. We say no more. We say too much work. We say show me the better way. Just like we got this thing once upon a time, right? Like, ooh, life is good. It's simple. You got the same thing today. No more infinite number of rectangles. You want to evaluate this? Super. Here's all you're going to do. Find an antiderivative. Plug in b. Same antiderivative, plug in a. Subtract the 2. Big F of b minus big F of a, where f is any antiderivative of f. That's all you got to do. How long did it used to take you to do this kind of a problem?
2-3 minutes.
Okay, 2-3. We're pretty sharp with it after a while, right? Yep. Once you get to like problem D, that one's going to take a little bit longer, right?
Yeah.
You're going to see how fast these go today, folks.
Wow.
What's the antiderivative of x squared? Right? The math symbol for evaluating is a line or like a bar. We're going to evaluate it at 2 and at 0. X to the third over 3 evaluated at 2 and 0. We're going to plug in 2 and we get 8 over 3. We're going to plug in 0 and we get 0 over 3. What is 8 over 3 minus 0 over 3? 8 thirds. That's the answer.
Wow. Me too.
What's the antiderivative of 3x squared? 3x to the third over 3, which is? X cubed. We're going to evaluate it at 4. We're going to evaluate it at 2.
Does it matter what side of the line the numbers go on? Like the 2 and the 4?
No, but I've never seen them written anywhere other than the right side. Are you looking to change that?
Well, I'm in 10, so I can't.
I plug in 4. What's 4 to the third? 64 minus 2 to the third is 8. Subtract those, you get?
56.
That's the exact area bounded underneath that curve from 2 to 4.
You are in calculus.
Not bad, huh? Maybe you should think about it in terms of area under a curve. What does that shape look like? Yeah, so if I look at that shape,
Sounds like an airplane.
recognize that I'm finding it at 1 or from 1 to 2. That is the area I'm looking for. And here's something that's going to come up in the next example. We say that area that's above the x-axis is positive area. Area that's below the x-axis is negative area. Okay? So we're going to try this in our calculators in a little while and kind of see how it works. But first, I have to find an antiderivative for 3 roots of x. So how should I rewrite 3 roots of x? 3x to the 1/2.
That's what I meant. That's okay.
So big F would be 3x to the 3/2. And here's where I try to save a little bit of time. Divided by what? Divided by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So that's where if I ever have a fraction, I always multiply by that reciprocal. Notice that the 3's drop out, don't they? And you end up with 2x to the 3/2, and we're going to evaluate that at 2 and at 1.
It's okay.
Okay?
I wrote them on the right side this time.
Good. I'm going to plug in 2. 2 cubed, 8. Square root of 8, 2 roots of 2 times 2, 4 roots of 2. I plug in 1. 1 to the 3rd, square root, times 2, 4 roots of 2 minus 2. Take out your calculator, let's investigate.
No. That's like doing 4x minus 4. Can't do that. 4x minus 4 is 0. No, math folks, you're breaking the math rules. You're right.
Math is fake.
It is.
I really have to
Oh
look
my
at that
gosh.
later.
All right, so I'm going to go into y equals, and I will type in 3 roots of x. You're not allowed to do this, just on the calculator on your test, okay?
Check it by this.
You can check your homework this way.
Can I check the test this way?
Nope.
What?
On the
You're
test, you
smiling?
may not press second calculate on this
You're
test.
smiling, so I'm gonna pretend like you're lying.
Okay, you go ahead and pretend, I'll fail you. So, we go second calculate, and I choose number 7,
So we can't do this for any of the problems?
not on the test. And we're going to evaluate from
1,
1
2.
to 2. And it gives me 3.656. Notice it's drawn the areas I expected it to. And if on your calculator you were to take 4 roots of 2 and you were to subtract 2 from it, see if we get that same value, and in fact we do. Okay? So we're finding that rather quickly. And just note that we talked about how long would it take us. Do we have do we have something that we can substitute in for our Riemann sum for a square root piece? Absolutely not. We were limited. If you notice, all the problems I gave you either had like a constant of 1, or it had x, or it had x squared, or it had x cubed. That's all we limited to. Anything outside of that, we had no way of finding. Yeah.
How many decimal points do you want us to go out? 3.
3.
Okay.
Okay. Let's type in the next one. We're going to end with this problem. We'll pick up the next 2 tomorrow. We'll be given the rest of the hour to work on that assignment. Hannah, could you please read off the problem to me?
X to the 3rd
Okay.
minus 2x squared plus 2x minus 3.
So what I'm interested in is I know that this is a cubic, but I know that the cubic sometimes is below the x-axis and sometimes is above the x-axis.
Yeah,
I
and
messed
that's
up.
wrong.
Okay.
It's just x squared, not so you raised it to
So I got to get rid of that.
Sorry.
Jojo, are we okay? Okay. So I'm going to calculate that area, number 7, and I'm going from what to what?
0 to 1.
So I'm going to go from 0 to 1.
Negative.
So you tell me, is this area above the x-axis or below the x-axis? The entire time, isn't it? So on your homework assignment tomorrow, I'm going to have you, you don't have to, it doesn't have to be a perfect graph, but I want you to sketch a little bit of the graph to understand what area is positive and what area is negative. Notice if I would have calculated this number 7, and instead of going from 0 to 1, if I would have gone from 0 to 2, as you can see there, we have both negative area and positive area. Does the total amount end up being positive or negative? Negative. There's more negative area than there is positive. By the way, you asked about application the other day. If we were to, there's tons of application, and do a good job explaining the other day because I was trying to put in context so you guys would get. It turns out that that total accumulation of area ends up being the total distance that we traveled to the left. And this positive area ends up being the total distance we travel to the right. And that thing ends up being our total displacement. So you are going to apply this in a really cool way that we'll see as well. So let's end with this problem right here. We know what it looks like. It is a cubic. And we had to type this one in our calculator because we didn't know exactly what that graph looked like. That's a representation of our area. We can appreciate that problem D would have taken us a good probably 10 minutes at least to go through if we were to do this by hand. So what's the antiderivative of x cubed? X to the fourth over 4 minus x to the third over 3 plus
2x squared over 2, so just
x squared minus, what is it that you take the derivative of to get 3x? I'm sorry. What is it that you take the derivative of to get 3? 3x. Okay. And I'm going to evaluate at 1 and at 0. So I plug in 1 and I get 1/4 minus 1/3 plus 1 minus 3. I'm going to find a common denominator of 12ths. And I have 3 over 12 minus 4 over 12 plus 12 over 12 minus 24, 36 over 12. So I have 3 minus 4 is -1. -1 plus 12 is 11. And 11 minus 36 is -25. That's the exact area.
Can we just, oh, never mind.
In economics, that may represent, instead of a profit, that may represent a loss over the course of a year as we calculate the net earnings, so to speak.
What about 0?
What would happen if we plugged in 0? You would get 0. That will change as we go to example E tomorrow. So these two examples are a little bit different. If you want to start some of your assignment, you can. But without a doubt, you're going to be given a lot of time to work on that tomorrow. Question, Hannah?
So technically, if it would be big F of B minus big F of A, would it be 0 minus -25 over 12?
No, B is the number on top, A is the number on bottom.
You're right.
Better?
Yep.
Excellent question.